Okay, welcome back, and let's continue the discussion on the mixture fraction kind of model. So, we have looked at the basic system like Boxman kind of flame and what happens when we have single step reversible and irreversible chemistry, and whether we have a infinitely fast chemistry or finite rate effect. We have seen how it changes, and we establish a simple equation for mixture, mass fraction, species mass fraction, and the temperature as a function of Z. And then finally, we got the relationship between the enthalpy and mixture fraction. Now, we look at the mixture fraction in turbulent flame. Let us say we start with an Rans kind of framework. So, we have mixture fraction, or rather this is our instantaneous, which is sort of affected due to the turbulence, and then you divide that on two components, one is the mean and one is the fluctuation. So, this is mean plus fluctuation, and the mean value one can find out, it could be ensemble average, this is in Reynolds average for number of sample and Zn. This we have repeatedly discussed again and again, that the how we can obtain the mean values and all these things. So, now when you talk about the reacting system, one of the important aspect of is that we have to consider the density weighted mean, and the density weighted mean for mixture fraction would look like rho z by rho, and then the fluctuation in density weighted average would be z minus z tilde. So, this is what we will be using for density weighted system. Now, once we use this density weighted average in Rans framework, our mixture fraction equation will look like that we have convection term, unsteady term, convection term, diffusion term, and as we have already seen, mixture fraction equation is free from any chemical source term, but due to this averaging we come across a term which is the scalar flux term, and that remains unclosed. So, this term is sort of unclosed, and this is one of the term what requires to be closed, and using gradient diffusion assumption, the simplest way one can close is that it is a rho thermal diffusivity to del z bar by del z. So, this is an one of the best way, and as long as there is no counter diffusion present, this works for a large number of flows. So, there is no issue associated with that kind of situation. Now, then when you use this, the closure approximation in this particular equation, this will come down to this equation under Rans framework. Unsteady term, convection term, this is the total diffusivity. So, this d plus dt is effectively the effective diffusivity. So, d is molecular and dt is the turbulent diffusivity, which is closed from the using the eddy viscosity and the turbulent Smith number. So, then these equations in Rans framework looks completely closed, and we can now solve this transport equation and then find out the evaluation of Z, which in turn allow to calculate the species and temperature profile inside the domain. Now, how do you obtain this mean property? So, that is an important question, because we have transformed our system from the local space to mixture fraction space. So, this for example, this is our flame front, let us say this is our flame front, and this is in flame normal analysis. So, our transport equation is in physical space, this is a Z equation, but and it is free from source term, and we are not solving mass fraction and all these things. So, those equations, the equation for the mass fractions and temperature, they are solved in this normal space, which is essentially the mixture fraction space. That means they are taken as a function of Z, and they are solved there, where individual mass transfer equation and that variation in one dimensional front is calculated, and it is done at the pre-processing stage or pre-computed and stored those information in a form of table. Now, while we are solving in the physical space this evolution of the mixture fraction, using that information we can use that table to find out a particular species and temperature. This is similar to the approach that we have discussed for premix flame, like an progress variable kind of approach, and what it allows that you require some probability density function, which is again and shape of the distribution would be assumed, which is called presumed, which we have seen in the BML model and other model, presumed PDF. So, one can now look at that the probability density function approach also has two different categories. One is the presumed shaped PDF, and which is also applied in both laminar flame, premix flame and non-premix flame, and there is another one is the transported PDF approach. Transported PDF is also theoretically applicable to both the regime, but it is more reliable or it requires tuning for each of these regime to use properly. But dimensional wise, transported PDF extensions are quite expensive. It is a heavy dimensional and that is why we solve in a hybrid approach, where you solve mean flow field in the Eulerian framework, and the transport equations of the probability density function is solved in the Lagrangian framework. Compared to that, when you look at this presumed PDF, it is much simpler, much easy to implement, and it is quite faster. Now, what happens? So, our mean species mass fraction will be integrated over equilibrium mass fraction, which is a function of z, as I explained here, and the probability distribution function or density function fz dz, and Fabre average mass fraction would be equilibrium mass fraction, which is a function of z, and Fabre average density function. So, the Fabre average distribution function would be rho z by rho bar fz. Now, if you look at this z which comes in, this is your oxidizer Z0, this is fuel Z1, they come in. So, at this particular location, if you look at the probability distribution function, at this location this will look like this, because this is more close to the oxidizer side. This is, you can see some distribution of Z, here you can see some distribution, this is, you see a Gaussian distribution. So, there are different probability distribution function in the field. Using this distribution function and the information of mass fraction, which is a function of Z, one can find out the Fabre average mean mixture fraction. So, if you go to the equilibrium flamelet model under turbulent condition, what one has to do at any location x, you can find out the mean values, and then you can find out the mixture fraction, or the using the information of the mixture fraction, you can find out the mass fraction or the Fabre average mass fraction using the equilibrium information of Z and the probability distribution function. So, this is what you get as a final result in the turbulent flame. And similarly, Fabre average temperature, which will be the temperature as a function of Z. So, it includes the effect of turbulent movements of flame position, but not finite rate kinetics, because our equilibrium information is like this, where oxidizer comes to at Z stoichiometry, whether Z, this is fuel, this is oxidizer, and our temperature can go like this. So, this is our temperature along Z stoichiometry. So, these are all Y fuel, Y oxidizer and T, they are function of Z only. When Z is solved, using that and probability density function, we get this, and rho 1 by rho bar can be equated as 0 to 1 by, which is also a function of this, which will be the connection between Now this is called the assumed shape PDF method or presumed shape PDF method. So in turbulent flow, the Z, the mixture fraction which is in the physical space, that is fluctuating because under the effect of the eddies. Now the probability density function of Zx has to be found. Now once we assume that PDF, the shape of the PDF is assumed, but mean and variance have to be calculated. So this is one important thing. So the equation along with your mean mixture fraction, one has to look at the variance. This is what we have also, it is a similar approach in a way one can think or correlate with the Z equation or level set approach that we discussed in the frame of premixed flame, where when you want to bring in this effect of turbulence and the interaction with the small scale structure and the large scale structure at different regime, you have to solve the variance of the G equation. Similarly here we have to also solve the variance of the mixture fraction. So we have two systems, one is the mean mixture fraction and the variance, which is represented as G. So these are the two transport equations that we get, one for the mean mixture fraction which is free from again source term and the D effective is D plus dt, and for the variance equation we get the similar up to this unsteady term, convection term, diffusion term, but then we get an production of Z variance and the dissipation. So these are the two terms which we come across when we derive the mixture fraction variance, and this guy is dependent on the mean mixture fraction because this is a gradient of mean mixture fraction and that square, and the dissipation term depends on some time scale ratio C phi and the turbulent time scale ratio, so that allows some sort of an ratio between these two that. So that is what one can get. Now it comes to the point how you define your PDF function or probability density function which is in presumed shape. So the one which is quite popular in literature, the definition is in gamma function. So the fz of z is defined as gamma of a plus b by gamma a gamma b z to the power a minus 1 minus z b to the power 1. Now here we use the value of mean mixture fraction and the variance. B is defined at a by z tilde minus a and a is z tilde minus 1 by z by g minus 1. So we need information of both z and z variance which we get from the transport equation, or rather the in the physical plane, physical space solution of transport equation. And now you can see in the physical space as these guys are evolving, because they have an unsteady effect, they have convection, they have diffusion, and G also has some source and term. So their evolution is not going to be very unique. They would be quite scattered, there would be effect of turbulence, and once you find or get that evolution pattern, using that you can find out this B and A, every location in the flow field, and then you can estimate that probability density function for that value of Z and Z variance, and then using that you can find out the mean things. So this is one of the example which has been taken from a Delft burner, where it is a laboratory scale natural gas burner. This is where CH4 is burning, and you can see, and these are beta function, and the ratio of gamma is A by Z tilde, which is Z tilde minus 1 by this, and it is a different shapes of the mixture fraction PDA found in different region of the flame. So, you have this region, other region, and you can see the different shape. So, that means this distribution function, since this is strictly a function of Z variance and Z tilde, their evolution will dictate how this Fz is going to look like. So, this is an important information one can have. Now, to complete this part of the discussion on the equilibrium flamelet model, so what you can see, this is a case for infinitely fast one step reaction. That means you have fuel plus oxidizer to get product. So, this is infinitely fast reaction. So, this picture, rather this whole thing will give you a complete idea about how the whole things are handled in the RANS framework. So, in Eulerian phase or framework, you solve pressure, velocity component, mixture fraction and variance, and which also in connection with your turbulence variable, whether k, epsilon, omega. So, all these mean flow fields you solve in the Eulerian field. Now, using this information of Z and Z variance, you can find out the probability density function, which will look like something like that, which is an essentially a gamma function. So, that gamma function you can estimate, and you get an for a particular location, particular instant of the time, this would look like this. Now, from our equilibrium calculations, we have a local flame structure where oxidizer becomes 0 at Z stoichiometric, fuel becomes 0, because this will vary from 1 to 0, oxidizer will vary. So, this is a profile of oxidizer, this is a profile of fuel, and this is a profile of temperature, which are strict function of Z. Now, we use this information of local flame structure and probability density function, we get the mixture temperature. Also, we can find out YF and YO. Using this, we estimate the mean density. Now, this mean density has an impact or effect of the temperature due to reacting system, and that is fed to the Eulerian framework. Now, again the Eulerian system is solved, and next instant of time, depending on these values, we do the same thing. So, this goes in a loop. So, that means the coupling between these, so you can think about there are two stages of the whole business or two systems. This is split into two parts. One is this mixing part, and this is the reaction or equilibrium kinetics part, and they are connected between these through the mean density, because mean density is the term which actually connects this Eulerian mean flow field calculations, because that has all this density and other side is the local flame structure. So, that fairly give you an idea how your equilibrium assumption or equilibrium flamelet model works, and that is simple enough to be implemented. Now, coming back to this picture, this is what our flamelet model where it belongs. It is a flame normal analysis. That means you actually convert your these things along this normal space. Now, we are discussing about system of non-premixed flame. So, that is what one can use. Now, something more about this mixture fraction, this we have already that fraction of the mass present locally, and this is how the equation looks, and the inlet of the air and fuel. Now, the question here is that can it be expressed in terms of measurable quantities? That is what is quite important that how do we estimate these things in terms of some quantities which are measurable. Now, we use the definition of the Lewis number. So, the Lewis number for individual species would be dH by dim, where this is mixture thermal diffusivity, species diffusivity with respect to mixture. Now, it is lambda by dim rho Cp. So, the dim is 1 by LEI lambda rho Cp. Now, this will be the species mass fraction equation, unsteady term, convection, diffusion, source term. Now, we convert that thing and use the information of the Lewis number, we get that this is 1 by Lewis number lambda by Cp. So, basically this particular term is kind of replaced with this. Now, once we do that, what happens? So, we take a situation again, that single step kinetics with irreversible reaction, fuel, oxidizer and product. Now, we find out the scalar without the source term. So, that means ZUN, which is defined as nu 0 W 0 YF and nu F WF Y0. This is how it is defined, and what we can see now, we multiplied this particular equation, this is what we got using the Lewis number. You multiplied with first nu 0 W 0 and this is the fuel mass fraction or mass transfer equation, and the second one, which is the oxidizer mass transfer equation. So, we multiplied this one with the fuel nu F WF, this is nu W 0. From this one to this one, if we subtract, so we get del rho Z by del T del dot, this is what it is. So, the diffusivity of the fuel and oxidizer are equal, stoichiometric values are. So, this case we are assuming that dF and dO they are same. Now, we construct the mixture fraction. So, this is a normalization to ensure the boundary condition. Now, this is the oxidizer side, this is the fuel side of two stream. Now, this would be ZUN minus ZUN2, ZUN1 minus ZUN2. Now, ZUN is nu 0 W 0 YF minus nu F WF Y0. So, which we can write nu F WF SYF minus Y0, ZUN1 equals to nu F WF minus 1, ZUN2 nu F WF minus 2. So, what we get, Z equals to S SYF minus Y0 plus Y02, SYF1 plus when the inlet one is fixed to fuel inlet and that is other one to oxidizer inlet. So, we get an expression for Z which uses the mass stoichiometric ratio, which is nu 0 W 0 by nu F WF and the stream, the mass fraction of the two stream. Now, if you have detailed chemistry, then how do we actually construct this mixture fraction? So, this is a very known formula, or it was derived by Professor Billiard. This is a scalar without source term, but the species molecules which are component or has elements of atom C, O, H, N. Let mu Kj denote the number of atoms of element K in molecule of species J. So, we go by the elemental mass fraction definition, which is for a element k of a mixture of species is given by ZEK summation over all mu kj WEK by Wij. Now, the whole idea is that elements are not destroyed by chemical reaction, therefore, the element mass fractions are scalar quantities without chemical source term. So, this is an important. Now, in the diffusion, species is described by the diffusion coefficient relative to the mixture fraction and the diffusivity of all contributive species are equal. The element mass fraction also has the same Lewis number. So, this is an important observation. In general case of non-equality Lewis number, the element mass fraction has more complex diffusion properties depending on species gradients. So, that is what it has. Now, we can have a stream 1, stream 2, and we can normalize that thing. So, Zk is a elemental k minus at second stream the elemental k by at the first stream to the second stream. Now, when the diffusivity of all species same, so the mixture fraction based on different elements are also become identical. So, that is another thing that would happen. Now, thing is that how do we extract the mixture fraction from the experimental data set. So, there are Raman-Raleigh measurements which provide the simultaneous data on major species, but that is not sufficient for a good approximation of the element mass fraction. So, what happens that one linear combination of element mass fraction can be used, like that unnormalized mixture fraction equals to gamma C ZEC, this is for carbon atom, gamma H ZEH, this is for hydrogen atom, gamma O ZEO, this is for oxygen atom, gamma N ZEN for nitrogen atom, and then we can normalize this with Z unnormalized minus unnormalized at second stream to unnormalize the first stream to second stream. So, this is at the stream 1 and stream 2. So, this would be ZUN1, this is ZUN2. So, one can define the stoichiometric condition for hydrocarbon combustion and inlet nitrogen. So, it would be ZEO by WEO equals to 2 ZEC by WEC 1 by 2 ZEH by WH, and the proposition the Bilger proposed there that different these things. So, gamma C is 2 by WEC, gamma H is this is as per Bilger's definition. There is an nice article on this, how you can find out this mixture fraction or elemental mixture fraction like this. Gamma O would be 1 minus WEO, gamma N 0. Now, once you use this information here, you finally get unnormalized stoichiometric Z is 0 even in the presence of differential diffusion. So, you can see not necessarily you have to actually assume that equal diffusivity, even for non-equal diffusivity you get these things to be 0. So, we will stop the discussion here today and continue these mixture fraction based things in details in the next lecture.